Now let's move on to the next application of vector analysis, which is all about divergence. Now if you have a vector that is specified at any point in the region or space, we could say that this region forms a vector field. And if we do have some scalar quantity at each point in a certain region, then we know that at this space, the region forms a scalar field. And that's the same way in divergence. If we have, for example, this fluid mass, and we want to determine the component at each point, then we could say that it will form a vector field. That's why from the scalar quantity that we have in divergence, we take the dot product of that using the nabla operator of any vector function or any vector quantity, then we'll be able to get a scalar function or scalar quantity. That's why for every vector field that we have, if we take the component of each of them using the dot product of the nabla operator, then we'll be able to get the divergence of that, which is actually a scalar field. So to give you an idea again of the nabla, this is identical to this expression. And again, once you add the component of each vector field here, then you will be able to get this kind of expression for the divergence. Now if you have the dot product, you just have to have matrices that have the same number of columns and then row, and then remember you will be multiplying each of them with the respective column that they have. So it's like the first column multiplied to the first one of the other vector field, and then this one is for the other one. So it's like the first for the first, and then second for the second, and the third for the third. That's why you will be left out with this partial derivative of component 1 with respect to x, and then the partial derivative of the component 2 at j region with respect to y. And then as you can see, this I hat becomes I squared, and then the j becomes j squared, and then k becomes squared, and then this collectively becomes 1. That's why this expression for the divergence can be simplified further without any direction, and that's why the divergence of f becomes a scalar field. Now let's try to solve problems involving divergence so that we can get a good understanding of how it works. Okay, so the first one is we need to find the divergence of z, which is a vector quantity. And again, as I've said before, the dot product is simply taking the product of each of them. So by taking the partial derivative of this expression with respect to x, and then this one is with respect to y. So with that, we take the partial derivative of f1 with respect to x, and then we add the partial derivative of 2 with respect to y, and then of course the partial derivative of 3 with respect to z. So in this case, we have cosine of xy, so that's negative sine of xy, and then the derivative of that with respect to y is times y, and then of course minus 1. And then we add, so this is for the first term, and remember we don't add the I hat because this is a scalar answer, a scalar quantity. So the derivative of sine h to xy with respect to y, so that is actually equal to cosine hyperbolic and then 3xy, and then times 3x. And then of course we don't have to add j because this is a scalar quantity. Now we can actually add or simplify this further if we can do something like that. So we have actually negative y sine of xy minus 1, and then we have plus 3x hyperbolic cosine of 3xy. Okay, so this is our final answer. So just remember, you just have to take each component, look at each component, and then differentiate that with respect to the direction that you have. So for the I direction, you differentiate it with respect to x because that's where our direction lies, and then the same thing goes for j and then k. Okay, so I think we're done. And then for number 2, we need to find the divergence of u, given that this is our value of u, and this is a vector quantity given by this vector notation. So for this one, we need to take the partial derivative of the first component with respect to x, so that is the inverse sine of x over y. So that is simply 1, let's just have the divergence of u is equal to 1 over the square root of 1 minus x over y, and that is squared. Okay, so this is for the first term, and then for the second term, we need to differentiate this with respect to y. So plus cotangent is actually cosecant squared negative y to the x, and then the derivative of y to the x taking y as the independent variable, so that would be times x raised to, times x times y raised to x minus 1. Okay, and then for the last one, what we have here is plus, we add the last term, which is actually the partial derivative of this expression with respect to z. And as you can notice here by inspection, we can see that this is a product rule. So we have negative z. So I have negative z times the derivative of ln of x raised to z is simply 1 over x to the z, and then the derivative of x to the z, knowing that z is the independent variable and x is constant. So x to the z times ln of x times 1. And then by product rule, we add the remaining, so that is ln of x to the z, ln of x to the z times the derivative of negative z, which is negative 1. Okay, so with this, the divergence of u is equal to 1 over the square root of 1 minus x squared over y squared, and then we have minus xy to the x minus 1, and then cosecant squared y to the x, and then I think this should be minus 2 or z. Let me just check if it's 2 or z. I think it's z. So minus z. And then this one is x to the z as well. So this cancels out, and then we're left with z ln of x. And then we have minus ln of x to the z. Okay, so that is our final answer, and I hope we get the same result here. Actually, we have the same result except for this, because I actually forgot to do chain rule here, and that's my fault. So we have x over y, and we need to differentiate that with respect to x, so we need to actually multiply this with 1 over y. That's why we do have also y here. Okay, so that's correct. That's the correct expression for this one. And then you can also simplify this further by adding these two. So we get 1 over y squared of 1 minus x squared over y squared, and then minus, that's xy raised to x minus 1, and then cosecant squared, and then y to the x. And then we add this. We can add this because remember that this is z, so we can place that at the exponent of x, so that becomes ln of x to the z, so we have minus 2 and then ln of x raised to z. Okay, so that we can get the same exact answer as the one in your module. But anyway, you can just leave it right looking like this one. It's just the same, but just to give you idea of how it happened in this case. So I forgot to do 1 over y here, so just insert that in your solution, because we still have to differentiate x over y. I actually forgot that. Now I'll be solving for 4 and 5. I'll leave number 3 to you because it's just the same concept, taking the divergence. Because I'll be doing this since it has this gradient of s and then the divergence. Okay, so for problem 4, as you can see here, we need to take the gradient of s first, and then we need to take the divergence of that gradient. So basically, what we have here is we need to first find the gradient of s. So we just have something like this nabla s, and that is actually equal to x, taking the total differential with respect to the partial derivative and then incorporating the direction. So with that, we have actually 2xy, and then we add 3yz, and then minus, we don't have any x, so that is the I direction. Okay, so this is our I direction. And then for the j direction, we have plus x squared, and then we also have plus 3xz or zx, and then minus 2y and then z. So this is actually the j direction. Then we add again for the z direction, we have 3xy and then minus y squared, and this one is the j direction. The k direction. Now from this expression, we need to find the divergence, so that is simply the dot product of the gradient of S. So this is how you represent the the divergence of gradient of S. So this is equal to, so we first take the partial derivative of this expression with respect to x. So that is 2y, okay? And then for this one, it's with respect to y. So that is plus, I think that will just be negative 2z. So that is negative 2z. And then for this one, with respect to z, so that is actually equal to 0. So in this case, we have the divergence of the gradient of S is actually equal to 2y minus 2z. Okay, so that is our final answer. And it is very simple, starting from this kind of long answer. Okay. Now for number 5, we need to show the y component of the divergence of the flow of compressible. So when we say compressible fluid, we have the density, and then the change in the velocity with respect to time is not equal to 0. And the fluid in terms of molecular transfer, tau, and we note that the molecular mass transfer or the molecular transfer flux enters at any point along the axis. So imagine if you have a pipe, and then you have this flow into this pipe. So the molecular flux is entering at any axis that we know. So it's like the x and y, z. So that's it. And then the equation of the molecular transfer flux is given by this general equation, where tau is the vector function of I, j, and then k. So we need to find the expression in terms of our y component divergence. So from this, let's just copy this, I think. So if we copy this first, then we can proceed with the solution. So having known this expression, let's just leave this density dv over dt at the left. We won't do anything about it first. And then we have this. This is the operation wherein we need to take the dot product of tau. And this is actually the nabla operator. So that's taking the divergence of this tau. So with this, we know very well that that is the negative of this tx of I, and then we know that this is tau. So basically, if we're talking about the y component, you should understand that the one we're talking about is the tau component at y. So in this case, even if this one is coming from the x-axis, it's just we're talking about the mass transfer flux from y. This is kind of difficult when you start studying momentum transfer and knowing that you don't have any knowledge about this, but you just look at the pattern and you'll just understand how this simply works. So we start with the divergence. So it's just taking the partial derivative of this component. So that's partial t sub x or tau sub x with respect to x. And then we don't have any direction here. So we add the partial derivative of tau with respect to y, and then that should be differentiated with respect to y. And then we have partial tau of z with respect to partial z. And because this is just the y component of our tau, we need to actually multiply this with our component at y. So we just have to attach that y at the end of all these tau expression, so that you'll understand that even though all the mass flux or the molecular transfer comes from all the axes, we just have to take the y component at any direction. Okay, and then the next one is that we need to find actually this one is the gradient of the pressure, but actually we don't have any idea of how the pressure looks like. So it's just like taking the pressure that is kind of coming from the y component. So with that, that's just taking the partial derivative of p, of course, with respect to the component at the y region. So that's how it goes for this gradient. So you might be thinking, how is it not something like p sub? Because you might be thinking it's I and then j and then k. But in this case, we don't have any we don't have to add those direction, because we know very well that we're talking about y component here. And then we have plus density g. So we just have to change this acceleration due to gravity with respect to the y component, so just add y sub y on that region. Okay, and now what do we do with this dv over dt? So this is the total differential of the change in v and then the change in t. So this is like having all the velocity profiles at any direction that you can think of. So now to work on this dv over dt, we can see this as if we have velocity, and then the general expression is that this velocity becomes, at any point we have vx and then vy and then vz. So this is all the velocity profiles that can move at any direction, but each of them would also be differentiated, of course, as a function of its direction ijk. So it's simply like x, y, and then z. So each of them we have x and then y and then z. Okay, so it looks the same. The tree diagram is kind of a long diagram, and then each of them is actually related, of course, to the time. So we have something like this kind of tree diagram that's very complicated. But what we have to be reminded this is that if we're talking about the y component alone, so we know for a fact that we need to find all of these x, y, and z. So with this, to express this in terms of the velocity profiles alone, we just take y. The movement is going to x, y, and z, so we just add that, and then we move towards the x, y, and z direction, and then of course for t. Therefore, this dv over dt, which is the total differential of the velocity with respect to time, is simply equal to the change in the partial velocity of y, or v sub y, with respect to t. So that's how it happened here. So you skip with this v, capital V, because that's the general equation. So start with this one, and then we add this with the movement to any direction, so that is actually vx, so that's vx, and then at the I direction of y, so we add vy with the j direction, and then of course the last one is the vz at the k direction. So where do we get each direction of them? So what we have is to look at vy and then take the partial derivative of that in the expression itself, so that we're left out with the correct direction of each of them. So we have this equal to the partial derivative of y with respect to t, and then plus vx, and then multiply it with the direction. So that is the partial derivative of y with respect to the x component, because this one is the velocity profile at x component, and then we add this one vy times the partial derivative of vy with respect to the y component, and then we add vz times the partial derivative of y with respect to the z component. And in that case, this is the final expression of dv over dt. Okay, so in this case, we already obtained this kind of expression, and then of course we multiply that with our density. So this expression is equal to this one, and then you just have to equate them. Now you might be confused with this tree diagram because of having v, so you could just separate them as if it's vx and then vy and then vz. Just remember, when you have dv over dt, it's the general expression goes like this. We have the partial v of whatever the component is that you're looking for, and you add all the necessary component of vxi and then vy j and then vz k. Okay, and then the partial derivative will come from the component where the fluid is actually of concern. So that's just a shortcut way of finding dv over dt. Okay, so I hope that is a clear explanation, because this is still kind of difficult to explain when you don't have any knowledge in momentum transfer. This is what we call momentum transfer or fluid mechanics. But you just follow these guidelines or these rules that we do in momentum transfer. Just remember this general expression, and then just equate that to how we do divergence in this case. Okay, and I think that's the final example for divergence. Okay, and then we proceed with the curl or rotation. So whenever we have a vector function with components which are first derivatives and continuous in our domain, we could simply say that the curl or the rotation of that vector function is the formal determinant of this expression, which is actually the formal determinant from the vector function and the nabla operator. So what we have to do here is to just take the cross product of the nabla operator and then your vector function, whatever it is. And then with that, your cross product will yield to this kind of expression. And that's actually the determinant of this matrix operation. So to set up that matrix, you add all the direction here, and then you add this portion of the nabla operator, and then finally this component at each component. So if you take the determinant for this case, remember your determinant for a 3x3 matrix can be solved using cofactor, but in this case I'll just use the scissor method. So you just first take the product of this one, so that is actually the partial of f3 with respect to y, and then that's I hat, okay, and then you add the product of this traced by the curve, so that is actually partial f1 with respect to z, then that's j hat, and then you add again the one that will be traversed by this curve, so that's k f2 and then partial of x, so that's partial of f2 and then partial x and then times k hat, okay, and then you subtract the rest, so that is the product that will be traversed by this single line, so that's partial f1 with partial y k hat and then minus again, or you could just put a bracket and then add, but that's just being minus or subtracted. Is there a term minus? Anyway, so that's subtracted, and then we have this curve again, so we have the partial of f2 with respect to z, that's I hat, and then minus the last one is f3 and then j. So that's it's like, you know, drawing scissors, that's why it's called scissor method. And if you're not familiar with this, you might as well want to review your matrix in your algebra, so that you understand what I'm talking about. So that's partial of f3, and then I think that's j and then x, so partial x and then j hat. So with this, you can simplify this, knowing that we have I hat here, and then this one is I, so that's partial of f3 partial y, and then this one is f2z, so this one is that one, and then after simplifying, you will arrive at this expression. Okay, so it's something like taking the formal determinant of this expression, and then that's your curl or rotation. Okay, so what we have here is this expression, and then to solve for this, let's copy it on a different sheet. Okay, so right now we need to find the curl of z. So the curl of z can be represented in terms of the nabla operator and then the cross product of z, which is actually a vector. So what do we have here is cosine of xy minus x and then sine h of 3xy. And we know, you can always label that. We can say f1 is equal to cosine of xy and then minus x, and then for your f2, you have sine h of 3xy. And if you would ask me if I actually memorized the expression for the cross product, and the answer is no, I don't actually know the whole expression for the cross product. It's just that I used that formal determinant to evaluate this expression. But for this case, since I've already shown you how it is obtained from the formal determinant, I'll just copy this. Okay, you can just memorize this formula when you're finding it kind of difficult to do to find the formal determinant of this expression. The curl of the function f is equal to f3 partial y, but we don't have f3, so that becomes 0, and then minus the partial derivative of f2 with respect to z is actually 0, so that becomes 0i. Okay, so we're left with the expression which is just 0i, and then for j, we move forward with j, so plus we have partial of f1 with respect to z, and that is 0, and then for partial of f3 we don't have any, so we're left with 0j. And then finally we have k, the derivative of f2 with respect to x, so we have there, so we have cosine of h, that's 3xy, and then we multiply this with 3x. Okay, I mean 3y because we're doing a y here. So we have I mean x, so that's y. And then we subtract this f1 with respect to y, and then we have here actually, so that's sine, I mean negative sine xy, and then times x, okay, and then we have 0 here. So that is actually our k hat. So therefore our curl of the vector function f is actually equal to 3y cosine of h, and then 3xy, and then that's positive x sine of xy, okay? So finally, you can say that this is existing only, the curl can be seen only at the k region. So I couldn't show you because it's actually moving, but I want to attach a picture here where you can find what's actually happening in curl, or a link probably that will show you how this curl works. But it's like the movement is something like curling at that region, okay? So, or rotating at that region. So for number 2, we proceed with that. So number 2 is we need to determine this cross product of u, and then we have this expression of u. So we start with this f3 partial y, and we know for sure that that is 0. Then subtract 2 with z. So we have the second one is this one, and then z is actually 0. So we have I hat, and then plus. For this one, we have the partial of f1 and then z. This is f1, and then for z, we don't have any value for z. So that is actually 0. Okay. And then for the partial derivative of subtracting the partial derivative of f3 with respect to x. So we have f3, and then this one is with respect to x. So we do have, and we know that that's actually equal to minus negative z, that's a constant, and then times 1 over x to the z. So that's times 1 over x to the z, and then the derivative of x to the z, knowing x is not constant, but z is, so we have z times x raised to z minus 1, okay? And that is for our j hat. And then finally, for our k, what we have is the partial of f2 with respect to x, and we do have that's cotangent. So plus the derivative of cotangent is cosecant negative. So y to the x, and then the derivative of y to the x, we're differentiating with respect to x, so we know that this is y to the x ln of y, okay? And then we proceed with subtracting this with f1 and then y. So with that, minus sine inverse of x of y over y, so that is minus 1 over the square root of 1 minus x squared over y squared, because that's squaring x and y. And then I forgot this before, but now I won't. So that is, we multiply this with the derivative of x over y, y being the constant. So that's actually x times negative 1 times y raised to negative 2. Okay? So with this, this is our k hat. And simplifying this further, we will have the curl or the rotation of u, that is equal to, or the cross product would be 0 I, and then I think this should be plus, so plus that will be z squared over x to the z. And if this is x raised to negative z, we can say that that is x to the 0 over negative 1. And with this, it leaves the expression to x raised to negative 1, and then that'll be z squared over x, okay? And then that is j hat. And then finally, what we have here is this expression. We have y to the x ln of y cosecant squared y to the x, and that is actually negative. So we have negative. And then we have, I think we can simplify this further to minus, so that becomes positive, so plus, and then we have 1 over y squared, and then that is square root of 1 minus x squared over y squared. You can actually factor this out or place it inside the radical sign, but I won't do it again. but I will no longer do it. So we have k hat. Okay, and this is our final answer. Okay, so let's check on our final answer. So we have here 0 for I, and that's a vector notation, and then z squared over x, so you get the same answer. And then this one is negative y to the x ln of y cosecant y to the x, so that's correct. And then we add x over y squared. Oops. Let me see it. Okay, I actually forgot to write x. We also have x here, so we have x. Okay, and then this matches up, I think, x y squared. And then okay, so that's it for our curl. You know, it's not really that difficult when we solve for the gradient, the curl, and this divergence. You just have to remember what you're trying to partially differentiate, and with that on your mind, you won't get any mistakes in doing this. Probably the rewriting stuff, but the rest, they're just easy problem. Now, for number 3, we have the rotation of cosine of xyz log of y to z and then z. I want you to do this because it's just the same doing the concept of the curl and then this curl or rotation. Now, I'll be doing this number 4 because this is the curl of the gradient of s. Now, for this one, what we have is we need to take the gradient of s, and we know that it can be curled. I don't know if that's the proper term, but you can take the curl or the rotation of that gradient because it results out to a vector function. Now remember, the divergence and curl can only accommodate vector functions. And remember, the gradient can only accommodate scalar functions. But when you do something like the gradient, the result is a vector function. Okay, so I don't know if that's the correct. So if you take the gradient of a scalar function, the resulting is a vector. And then if you take the dot product, which is the divergence of a vector function, that is actually scalar. And then finally, if you take the curl of a vector function, that is also a vector function. So don't forget about it. This is the gradient, this is the divergence, and this is the curl. Anyway, let's proceed. So we take the gradient of this expression, so that is the gradient of s, that is equal to, we start with x, so that is actually equal to 2xy, and then we add, I think, 3yz, and then that's the I hat, and then we add for the j hat, so we have y, that's x squared, and then plus 3xz, this kind of looks familiar. I don't know. And then minus 2zy. Okay. And then that is for the j hat. And then we add for the k, so that's actually z. So we have 3xy. Then minus, I think, y squared. I think this is the one I used before. Anyway, so that's k hat. Okay, so this is our expression for, oops, that should be y squared. So this is our expression for the gradient, and we take the curl of this expression, and we know that f1 is equal to 2xy, then plus 3yz, and then for f2 we have x squared plus 3xz minus 2zy. And then for our f3 we have 3xy minus y squared. Okay, and then based on our general expression that we have here, I'll be copying this because I haven't memorized it yet. I don't actually memorize it because you can always do determinant form to obtain this expression. So with this, we need to take the curl of our function f. Is it f? S. So if it is s, then that's actually s. You substitute this f1 to s1 and then s2 and then s3. Anyway, it doesn't matter, really. You just have to get the correct answer because these are just labels or notations that you can use. That is equal to the partial derivative of s3 with respect to y. So this is with respect to y. So what we have here is 3x and then minus 2y. Okay, and then we subtract this expression with partial of f2 with respect to z. So z here is 3x, and then of course this one is negative to Z, I mean to Y. But if it is subtraction, then we have positive to Y. Okay? Or you could just use subtraction and then we have negative and then, I mean, negative and then positive here, and then we have negative here. Okay? So that's for I hat, and then for J hat, we have partial of F1 and then Z. So that is actually 3Y only. And then we subtract F3 and then X. So that is X. We have 3Y here, but we don't have any value for this one. Okay, and that is J hat. And then we add the last one, that's partial of F2 with respect to X. So that is 2X. Okay, and then plus 3Z from here, and then we don't have any X here. And then we have partial of F1 with respect to Y. So with this, with respect to Y, that is minus of 2X. And then this one is with respect to Y, so that is plus 3Z. Okay. So with this, as you can see here, we can just cancel this out, and this one, and then also this one, and then the rest. Okay. Which leaves us the curl of S. Actually, that's not the curl of S, but that's actually the curl of the gradient of S. My bad. So that is the curl of the gradient of S. So that is, we need to change this to the curl of, because that's a different story. The curl of the gradient of S. That is equal to 0I plus 0J and plus 0K. Okay. This can also be rewritten in the vector form. So that is 0, 0, 0. Okay. So this is our answer. And as you can see here, it can also be concluded that the curl of the gradient is always 0. So the curl of a gradient is 0. Of course, you're curling the same scalar function that you used in the gradient, and of course when you take the gradient of S, that will be a vector function that can be curled, so that will be always 0. Now you can always remember this pattern, and I'll be showing you that mnemonics that we used in vector analysis. So that is D, and then we have something like C and then G. That's DCG. Let's have a large font size. Okay, so this DCG can be viewed as if you take the curl of the gradient, so it's like having this arrow. Let me just use the correct arrow. So if you take the curl of the gradient, that will always be equal to 0. Okay, and then when you take the divergence of a curl, so that would be always equal to 0 as well. Now, how do we prove that? We can go back to this expression, and then we know that this one is the curl of this expression. We have a curl that's x sine xy and then 3y cosine of h of 3xy. You can try taking the divergence of this expression, and you'll notice that you will just get 0. So with that, I'll do it for you. So let's try doing this k. So if you want to take the divergence of this k, and we know that that's just k only, so I'll just have to use this and then differentiate this with respect to z. And then can you see any z right here? So therefore, we can say that the divergence of this curl is actually equal to 0 because you don't have any z here at the k value. So that's it for your shortcut. And then just to give you another idea, if you take the divergence of the gradient of course of the a scalar function, you'll be able to get the Laplacian or the scalar Laplacian of this expression. And then when you try to do something like you take the gradient of the divergence, because you can actually do that, because when we talk about gradients, we need to actually use a scalar quantity. And then if you take the divergence of a certain vector function, you'll be able to get a scalar function, and then it can be solved using the gradient. So with that, by taking the gradient of the divergence of a vector function, you'll be able to get the sum of the vector Laplacian. So that's actually the vector Laplacian and then the curl of the curl. So it's like if you take two curls of that same vector and then you take the vector Laplacian of that, then you'll be able to get the gradient of the divergence. Now for this case, if I ask you what is the scalar Laplacian of this expression, so when you have a scalar quantity, so you just have to take the divergence of the gradient of that scalar function, and then you'll be able to get the scalar Laplacian. So it's like you take the divergence of this scalar function. So this is actually equal to something like this expression. This reduces that quantity, and it's just the scalar Laplacian. So I think this is the figure that is very important, the DCG. And then you can't actually do something like you take the gradient of the curl. That's impossible because remember, the resulting expression for a curl is also a vector. So you can take the gradient of that, and of course you can curl the divergence because the resulting divergence of a certain function is a scalar quantity which cannot be curled. So this is the whole expression that gives us, and then you can't just do an arrow back to this. Okay, so with that, I think that's all for our vector analysis, and then I think the last part here is about the summary of vector differentiation, and this is what I'm talking about, the Laplacian. This is actually the scalar Laplacian. So if you take the divergence of a curl, the divergence of a gradient, then you'll be able to get the Laplacian, which is just simply taking the second partial derivative of of the whole expression with respect to x, and then adding that with y and then z. And of course, the resulting is not a vector quantity but a scalar quantity as well. So you can do that to get the scalar Laplacian. And then remember, when you take this one, the curl of the gradient, so that is 0. And then for this one, if you can see that the curl of a vector function vanishes everywhere in the region D in space, so we call this irrotational. It says also here that the scalar of the divergence of the curl is also 0. So in that case, the divergence of the vector U vanishes everywhere in the region space, and we call this solenoidal in this region. So remember, if we have a curl of the gradient that is 0, that is irrotational, and then this one is the divergence of the curl, that is solenoidal. So if we go back to our problem that we've solved, we took the curl of the gradient of this, so we call this irrotational. So let's call this irrotational. Okay, so had it been something like this one, I actually solved for this one. So this is the divergence of the curl. So this one becomes solenoidal. That's based on the description here. So, okay, I think that's it. And this is the identities of the scalar function and the nabla operator. I'm not really like forcing you to memorize this because we'll not be using this anymore. We just need to find the gradient, the curl, and then some of the properties that are that I actually used, and it just boils down to this 3 DCG and then scalar Laplacian, and then the irrotation and the solenoidal. So I think that ends our discussions in differential calculus. I hope you've learned something from me, even though this is kind of very fast paced, and this pandemic is still kind of difficult to be accustomed to, even though it's been a long time, and we all feel pressured. You feel pressured academics, and I do too as well, because sometimes I have to meet the deadline. I'm setting my deadline for myself, so it's kind of frustrating when I don't meet it. And anyway, we still have to move forward, I guess, and this is the last topic that I want you to give your last brain cells, probably, because I'm hoping actually that you've already had the mastery of differential calculus. But if you don't have, then you still have time. We start with the little knowledge that we have, and then we pile them up so that we can grow with the knowledge that we have, and then apply that in the more difficult situation. So in that note, I want to say thank you, and then as much as I want to see you all, it's not yet possible. So I'm hoping that I can share, I can still share my knowledge with you. And whenever you have questions, don't hesitate to ask about it, because I'm always free to, I mean, I'm not always free, but I can always spare some time. I'm reading your problem, or, I mean, academically. But if you want some advice, I can also give you. So thank you, and God bless you all. Stay safe, future engineers.